Welcome back, student. Now, today we'll discuss about the number of vacancies in a crystalline structure, and the distance, the interplanar distance between a plane and origin of the cube. Okay, already we discussed that this topic, but we just remind that uh, recall it actually. Uh, the topic is your that what is the number of vacancy created due to the uh, defect or due to due to point defect. Okay, as you know, there are different types of crystal defect are there, like point defect, line defect, surface defect, volume defect in a particular material. So there are point defect like vacancies, substitutional defect, interstitial defect. So there are so many others type of defect like Frankel defect, Schottky defect. So this type of defect are occurred. That defect basically zero dimensional defect. Okay, and that's why it's called point defect. And there are some atoms are missing from a particular lattice structure. If they are missing for a particular location of the crystal structure, then particular this type of defect is called vacancy. Okay, now if it is happens because it is not a spontaneous process, there are some energies, some thermal energy is activated, or some activation energy is required to transfer the atoms from the regular sites of the atoms. So there are some activation energy there, so that the a particular crystal structure are there, when the crystal in the crystal structure a particular atom is missing from a particular regular site. So that type of energy is called activation energy. Now that activation energy generally designated, that is QV. Okay, here it is QV, that is your activation energy, that is 0.9 electron volt per atom. Means per atoms you have to require the activation energy, that is 0.9 electron volt, to create a of point defect or vacancies. Okay, so as we know that in a particular regular crystal lattice structure, the number of atoms missing, that is basically the what is the number of atoms that missing, that is NV. Okay, NV is equal to Ns e to the power minus QV by KB into T. Now NV is the number of vacancies in a regular site that can be created by the applying of by the applied the activation energy. Okay, or you can say thermal energy. Ns is the actual number of regular sites in regular number of regular lattice site, that is Ns, and QV, as you know, that activation energy or thermal energy, and KB, here Kp basically your the Boltzmann's constant, and T is the temperature at which temperature the point defect occurs or vacancies are formed. So, in this problem, what is given is that calculate the number of vacancies in copper. So, the material is given to you, that is copper. You have to calculate the number of vacancies at room temperature. So, at room temperature, you have to calculate the number of vacancies of copper. Now, assume Boltzmann's constant. So, Kb, Boltzmann's constant is Kb, as you know, that 1.38 into the power minus 23 joule per atom Kelvin. Okay, or if it is transformed into electron volt, that can be also 8.62 into 10 to the power minus 5 electron volt per atom Kelvin. And the activation energy that is given QV, that is is equal to 0.9 electron volt per atom. Okay, and temperature is given, that is 27 degrees Celsius, that is room temperature, and rho Cu, that means the density is 8.4 gram per centimeter cube, and atomic weight atomic weight of copper, that is ACU, it will be not CV, ACU, that will be 63.5 gram per mole. Okay, so these are the value are given. So you have to calculate the number of vacancies in copper. So this is the formula, this is the expression, because very important formula, because the number of vacancy that can create or generate, that is basically number of NV, number of vacancies NV is equal to Ns e to the power minus QV by KB into T, and all these terms already known to you, and the value of KB is known to you, QV is known to you, and T is known to you. Okay, now you have to calculate the number of regular lattice site, that is NS. NS is equal to NV into rho divided by ACU, is the number of atoms, that is basically Avogadro's number, okay, that is 6.023 into 10 to the power 23, and rho is basically your density of copper, that is 8.4 gram per centimeter cube divided by atomic weight, that is 63.5 gram per mole. If you put this value, you can get the value of Ns, which is basically number of regular lattice sites, Ns, okay, that is 8 into 10 to the power 20, I think 22, okay, 22 atoms per centimeter cube, okay. Now when you calculate the number of vacancies, now we put this here, M is equal to Ns into the power minus Kv by T. If you put all these values, Ns here, this one Kv is given to you in the numerical, Kv is also given in the numerical, and T is the room temperature, okay, that is 27 degrees Celsius or 300 Kelvin. Now if you put all these values, you can get the number of vacancies that can generate by applying of activation energy of 0.9 electron volt per atom at room temperature of copper, that is 7.4 into 10 to the power 7 vacancies per centimeter cube. So these are the number of vacancies that can generate, but this type of vacancy is very important in a particular materials, because crystal defect are generally used to improve the properties, because there are deformation. As you know, the deformation is the reason, because of there are dislocations, okay. Deformation is the main thing of a particular material when you apply load, because deformation is the result, but in between, in the inner part of the material, if you see in the small things in the particular material, so you can see that there are some dislocation or occurs, and due to dislocation movement, the deformation occurs. So dislocation also one type of defect. Similarly, the vacancy is very important, because to improve the mechanical properties. So all the times it is not possible. A defect is bad, but in material defect is basically it's very we also introduce material defect, like in case of electronics devices like p-type doping, n-type doping, because to improve the material properties like semiconductor, any type of material. So defect is very important, which is present in the material, or it can be generated by means of artificially also, okay. So these are the number of vacancies that generate, that is 7.4 10 to the power 7 atoms per centimeter cube, okay. Now let's take another numerical on the interplanar spacing. Already discussed that interplanar spacing, that means the plane, the distance between the plane of the plane and the origin of the cube, that is d, the interplanar distance d is equal to a by under root of a divided by under root of h square plus k square plus l square. As you know that interplanar distance d is equal to a by under root of h square plus k square plus l square. So where d is basically your interplanar distance of the atom and origin of the cube, because atoms are arranged in such a way, if you assume that atoms are arranged in a cubic structure, so the origin of that particular cube and the plane that generate a particular atom, okay, so that the distance, the perpendicular distance, that is d here, that is basically a is the lattice constant or lattice parameter, or you can say the distance between the two atoms in a cube, okay, that is a divided by under root of h square plus k square plus l square. That indicate actually in the particular Miller indices. We know that Miller indices are basically designated in a particular plane, that is maybe 2 1 1 1 2 2, so that indicate here h, k and l. Similarly h, k, l 1 1 1, that means h1 k1 l1. So these are the nomenclature that we use for in case of Miller indices. If the one plane is given to you, that means h is 1, k is 1, l is 1 also given. Similarly in this form also, in this numerical, you have to calculate the interplanar spacing, okay. So in this numerical, for BCC iron, so for BCC iron means the structure is given to you, that is iron, but that form, that is body center cubic structure, okay. And for body center cubic iron structure, you have to calculate the interplanar spacing, that means d, and diffraction angle for the 2 1 1 plane and set of plane. Lattice parameter for the iron, that is a here, lattice parameter, because A is equal to 0.2866 nanometer, and wavelength of X-ray, because as you know, and from the Debrag's law suggests that when there are two planes are there at all, the X-ray are plane there, so these are the plane A. So okay, so the X-ray wavelength is given to you, and Debrag's law suggests that 2d sin theta is equal to n lambda, right? 2d sin theta is equal to n lambda, where d is the interplanar distance, sin theta is your Debrag's or diffraction angle, and n is your the plane, actually the order of reflection, and lambda is your wavelength. So these are the values. These are the values is indicates your Debrag's law. Now for the BCC iron structure, calculate the interplanar spacing. That means the distance between two planes, the distance between the plane and the origin of the cube, and the diffraction angle, that is the theta. In an expression like 2d sin theta is equal to n lambda, in the expression the theta is your Bragg's angle, okay, or diffraction angle, you can say that. You have to calculate all two things. Now for this, two value are given to you, that is for lattice parameter of iron, that is 0.2866 nanometer, and the wavelength that is also given to you, that is 0.1542 nanometer. Now order of the reflection is 1. Now order of the reflection is 1. So that means the value of A is equal to 0.2866 nanometer, and lambda is 0.1542 nanometer, okay. And the order of the reflection that is 1, it is given to you. And the plane for the actually what you have to calculate the distance, the plane and the origin of the cube, that plane is given to you, that is 2 1 1, that means h2 k1 and l1. So in this case h2 k1 and l1, so the distance for interplanar spacing, that is d211, is basically a divided by under root of h square plus k square plus l square. The value of a is given 0.2866 divided by under root of h square is equal to 2 square, k square is equal to 1 square, and l square is equal to 1 square. So d211 basically your interplanar spacing, that is 0.1433 nanometer. And for the Bragg's law, as you know that 2d sin theta is equal to n lambda, and you know the value of d means here d211, and here d means d211, okay, the interplanar distance for the plane 211, and n is 1 and lambda is value is given, that is wavelength. If you put all these values, then you can get the diffraction angle, that is theta, that will be 32 degree 33 minute. So these are the interplanar spacing and the diffraction angle for the plane 211, okay. So in this numerical, a diffraction pattern of a cubic crystal structure of lattice parameter A is equal to 3.16 angstrom is obtained with monochromatic X-rays beam of wavelength 1.54 angstrom. The first line on this pattern was observed to have theta is equal to 20.3 degree. Determine this interplanar spacing and the Miller indices of the reflecting plane. Okay, now a diffraction pattern of a cubic crystal of lattice parameter. Now, lattice parameter A that is given, that is 3.16 angstrom, okay, is obtained with a monochromatic X-rays beam of wavelength that is 1.54 angstrom, okay. The first line on this pattern was observed to have theta is equal to 20.3 degrees. So theta is equal to 20.3 degrees given, and in the first line, that means the plane, that is the first plane where the X-rays are intact with that. So n is equal to 1. So you have to calculate the interplanar spacing and the Miller indices of the reflecting plane. Now, as you know from the Bragg's law, that is 2d sin theta is equal to n lambda, that is Bragg's law, and that is basically used to determine the crystal structure or crystallography. Okay, means crystal, means atomic arrangement of the crystal. There are deep Black's law, there's X-rays, so the different types of technique are there to identify this crystal direction as well as crystallography also. Now, as you know that 2D sin theta is equal to N lambda, and the angle in which the X-rays is incident on a plane of the atom in the first plane, that is 20.3 degrees given. Now n is 1 because the first plane, and lambda means the wavelength of X-rays wavelength, that is 1.54. So that's from these equations you can get the value of d. That means interplanar spacing. The d, that will be 2.22 angstrom. Okay. Now the second part of the numerical, now you have to calculate the Miller indices of the reflecting plane. You have to calculate the Miller indices of the reflecting plane in which the atoms are reflected. Okay. So as you know that d is equal to a divided by under root of h square plus k square plus l square. So d is the interplanar distance and a is the length of the cube or the lattice constant or lattice parameter, that is a, divided by under root of h square plus k square plus l square. So d is equal to 2.22. Fine. Okay, because you can get from this here that is d is equal to 2.22 angstrom, that d is equal to 2.22, and a here 3.16, that is your lattice constant, that is 3.16, and value of h square plus k square plus l square you have to calculate, because you have to calculate the Miller indices. How do you calculate? So you know the value of d, you know the value of a, so you know the, because you know the value, or you can get the value of under root of a square plus k square plus l square will be that 1.423, or you can say that near about under root of 2. So if you reduce, or if you neglect the square, if you get the square all in right side and left side, so you can get a square plus k square plus l square is equal to 2. Okay, so h, k and l, so there are some combination of values that you can get the value that will be 2. The satisfied condition is maybe that it may be 1, it may be 1, it may be 0. 1 square is 1, k square is 1, so 1 is 2, l is 0. So this is the first condition in which it can satisfy that h square plus k square plus l square is equal to 2. So 1 1 0, it may be one plane. Again, it may be also 0 1 1, I'm sorry, 0. So it may be one case, first case is h is equal to, I'm sorry, first case in this case is k is equal to 0. We assume that l is equal to 0, sorry, and h is equal to 1, k is equal to 1. Second case, h is equal to 0, k 1 and l 1. And uh, third case will be that h1, k0 and l1. So in all these cases, if you put these values here, you can get that h square plus k square plus l square is equal to 2. So this is the conditions in which you can satisfy that h square plus k square plus l square is equal to 2. So the effective Miller indices in which the X-rays are reflected on a plane, that is, it may be 1 1 0 or 0 1 1 or 1 0 1. So these are the corresponding Miller indices of the reflecting plane. Okay, and these are the interplanar distance. Okay, these are the interplanar distance, that is d, that is 2.22 angstrom, and this is your the value of Miller indices. Okay. Okay, thank you very much for listening and watching me, and good.